In this video, we are going to discuss about the mass transistor characteristics under static and dynamic conditions. So on completion of this topic, the students will be able to explain the electrical properties of mass transistor and they can able to draw the DC and transfer characteristics of the CMOS inverter. So next we are going to see about the VLSI integration levels. So here we have 6 integration levels. One is small scale integration, which is less than 12 gates per chip, and medium scale integration 100 gates per chip, large scale integration up to 1k gates per chip, and very large scale integration up to 10k gates per chip, ultra large scale integration up to 100k gates per chip, and gigantic scale integration up to 1 mega gates per chip. And now we can see the mass transistor. So in this mass transistor, here we can see the structure of the mass transistor. So this, as shown in the figure, this mass transistor contains 3 layers. One is metal gate electrode, the insulating oxide layer, p-type semiconductor. So this mass structure forms a capacitor with gate and substance, or this has 2 plates and oxide layer as the dielectric material. So this thickness of this dielectric material, we say that SiO2, which is usually between 10 nm and 50 nm. So here the carrier concentration and distribution within the substrate can be manipulated by external voltage that is applied to gate and substrate terminal. So now to understand the structure of mass, first we have to consider the basic electrical properties of p-type semiconductor substrate. So here so normally the concentration of this carrier in the semiconductor material is always following the mass action law. So here we write this mass action law as Np equal to Ni square, where this Ni is the carrier concentration of electrons, P is the carrier concentration of holes, and Ni is the intrinsic carrier concentration of silicon. So now if you assume that the substrate is equally doped with the acceptor concentration, electron and the hole concentration in the p-type substrate is Np and Pp. So normally this value is doping concentration is greater than an intrinsic concentration. And now to understand this mass structure, we are considering the energy level diagram of the p-type semiconductor, that is p-type silicon substrate. So here you can see the source, gate and drain. So gate electrode is there, gate dielectric, and an insulation is present. And now to see the structure and operation of Mosfet, here this Mosfet consists of the mass capacitor with 2 p-n junction, which is placed close to the channel region, and this region is controlled by the gate voltage. So to make both the p-n junctions reverse biased, this substrate potential, what it means, is kept lower than the other 3 terminal potential. So if the gate voltage will be decreased or increased, if the gate voltage will be increased beyond this threshold voltage, means then this inversion layer which is established on the surface and the n-type channel that is formed between the source and the drain, which will carry the drain current according to the VDS value. So here for different value of VDS, this MOSFET can be operated in the different regions. First one is linear region. So in the linear region at VDS is equal to 0, this thermal equilibrium exists in the inverter channel region, and the drain current ID value will be equal to 0. So now if small drain voltage, that is VDS values, is kept as constant or it is greater than 0, means a drain current is proportional to the VDS and it will start to flow from the source to the drain through this channel. So this channel gives a continuous path for the flow of the current from the source to drain. So this mode of operation we call it as linear region. And in the case of the saturation region, now if the VDS is increased, this charges the channel and the channel depth will decreases at the end of the drain. So for VDS is equal to VD sat, the channel in the charges in this channel is reduced to 0, which we call it as pinch off point. So this cross-sectional view of this n-channel MOSFET is operating at the edge of the saturation region. So this is found at the edge of the saturation region, or we call it as pinch off point. And in the saturation region, for VDS values greater than VDSAT, this depleted surfaces from the near to drain, and by increasing the drain voltage, this depleted region extends to the source. So this mode of operation is called as the saturation region, and the electrons coming from the source to the channel end enter into the drain to depletion region. They are accelerated towards the drain in the high electric field. So this is the operation of the MOSFET, and here we can see the voltage characteristics. So in this voltage characteristics, to understand this MOSFET, approximation of the channel is done. Without this operation, there is three dimension analysis of the mass system becomes so complex. So first one is the gradual channel approximation. So here you are considering the cross channel view of the n channel MOSFET in this linear mode. So here source and substrate are connected to the ground. Vs is equal to Vb equal to 0. So the gate to source and the drain to source voltage are the external parameters that control the drain current. This voltage is set to the voltage greater than the threshold voltage that will create the channel between the source and the drain. So as shown in figure, this x direction is perpendicular to the surface and the y direction is parallel to the surface. So here you can see here y is equal to 0 at the source end. As shown in this figure, the channel voltage with respect to the source is represented by Vc. So assuming this the threshold voltage Vto is constant along the channel region between this y equal to 0 and y equal to L, this boundary region of this voltage can be the total mobile charge in the surface inversion layer. So this is the operation that is happening in the linear region, and beyond the saturation region we can see that is this Vd is increased and the charges in the channel and the channel depth increases at the end of the drain. So this channel can reduce to 0, which called as the pinch off point. And in the gradual channel approximation, this channel is operating in the linear mode, and also this voltage is set to the voltage greater than the threshold voltage to create the channel between the source and the drain. So this x direction will be proportional to the surface and the y direction is parallel to the surface. So you can see in the diagram that is VA characteristics. So in this VA characteristics you can understand the current voltage characteristics of the MOSFET, and without this approximation, three-dimensional analysis of the MOS system becomes very complex. Quiz questions on the MOSFET transistor characteristics under static and the dynamic condition. First one, what are the necessary conditions for the different regions of operation in the CMOS inverter? Thank you.